Hi guys, welcome back to my YouTube channel. So today we are going to study the design steps of siphon aqueduct from the chapter cross drainage structure. So in this chapter we will study about the design steps of the siphon aqueduct. For the siphon aqueduct we have aqueduct are those structures in which the irrigation canal passes over the drainage, and siphon aqueducts are those structures in which when the HFL of drain is much higher above the canal bed and water runs under siphonic action through the aqueduct barrel, that will be the siphon aqueduct. So for the design stage of the siphon aqueduct, the first step is to design the drainage of waterway. For that we will calculate the weighted perimeter from the Lacy's equation. P is equal to 4.75 root under Q. Provide 6 to 8 meter of clear span between the aqueducts. So 8 meter we will provide. Now take the pier width of 1.5 meter. Calculate height of the barrel using Q is equal to A into width from the continuity equation. Also assume the velocity through the barrel is 2 to 3 meter per second. So you can just screenshot these steps of the siphon aqueduct, and we will use these steps while solving the numerical of siphon aqueduct. Now the second step. In the second step we will design the canal waterway. So for that provide the canal width 15% of initial width at crossing point. So whatever the width is given, we will assume the provide canal width 15% of the initial width at the crossing point. The velocity through canal must be less than the 3 meter per second. Provide a split of 2:1. In step 3 we will design bed level at different sections. For that we will calculate the total energy line, which is equal to P by gamma plus B square upon 2G plus Z, whereas P by gamma is the pressure head, this is the velocity head, and this is the elevation head. For open channel, the pressure head will be equal to Y due to the water level. Now the total energy line will be equal to this Y plus B square upon 2G plus Z. Water surface elevation will be equal to bed level plus depth of flow, that is Y. Energy line equal to water surface elevation plus the velocity head, where the downstream energy will be equal to upstream energy minus head loss. Now in the fourth step design of transition will be done. The transition for the contraction and for the expansion, we have the formula Bx is equal to Vn into Bf into Lf divided by Bn into Lf. This is the formula we will use for calculating Bx, whereas Bx is the width at any sections at a distance of x meter from the flume section. This distance Bf, Bx. Bn is the normal width of the canal, Bf is the width of the flume section, and Lf is length of the transition. Now we will solve a numerical based on this chapter cross drainage structure. So the given question is to design a siphon aqueduct if the flowing data at the crossing of canal and drainage are given. Discharge of canal, these are the data for canal and these are the data for drainage. So here discharge of canal is 50 cubics, bed width of canal is 30 meter, full supply depth is 1.5 meter, which is the Y that we have assumed for the pressure head. Bed level equal to 1.6 meter. Side slope of canal is 1.5 horizontal is to 1 vertical. High flood discharge of drainage is 500 cubics. High flood level of the drainage is given 107 meter. Bed level of the drainage is 104 meter and the general ground level is 106 meter. So now here, since here the high flood level of the drainage is 107 meter, which is higher than the bed level of the canal, which is 106 meter. So the siphon aqueduct will be provided here. High flood level of drainage is above canal bed, therefore siphon aqueduct is provided. So the first step is to design the drainage waterway. So here design of a drainage waterway. This is normally for 2 marks. Okay, so now while designing the drainage waterway, we have to first calculate the weighted perimeter using the formula P equal to 4.75 root under Q. So here P is equal to 4.75 root under Q, which is equal to 4.75 root under 500. Drainage cubics is 500, which will be equal to 4.75 root under 500 is 106.21 meter. Here, after calculating the weighted perimeter, provide 6 to 8 meter of clear span and the pier width will be 1.5 meter. For this, while providing the clear span, we will calculate 106.21, since we will divide the clear span of 8 meter each. So we will get 106.21 divided by 8, total number of 13. Okay, so we will provide less than this, that will be 12. We will always take one number of less pier. Okay, so there will be the total number of pier we will take will be 12 and the clear span of 8 meter each. So here provide 12 clear spans of 8 meter each and let the width of each pier be 1.5 meter. Now we will calculate the length of the waterway. So the length of waterway will be equal to this total 12 into 8 plus 11 into 1.5. So the formula is here x into 8 plus x minus 1 into this width 1.5. So using this formula you will easily calculate the length of the waterway, whereas x is the total number of the piers, that is 12 into 8, and subtracting the number of piers, that will be 11 into 1.5, the width of each pier. So the length of the waterway will be 11 into 1.5, that is 112.5 meter. Now we have assumed the velocity through barrel nearly 2 to 3 meter per second. Here taking V is equal to 2 meter per second, we get the area, whereas Q is equal to AV, so A will be equal to Q by V. So the discharge of the drainage is 500 divided by velocity is 2, which is equal to 250. Now also area is breadth into height, which is equal to 250. So the height of the pier will be 250 divided by the breadth, that is 12 into 8, which will be equal to 250 divided by 12 into 8, so 2.6 meter. Now after calculating the height of the barrel using this continuity equation, we will now calculate the actual velocity through the barrel. Now the actual velocity through barrel is equal to discharge by area, that will be Q by A, which will be equal to 500 divided by 2.5 into 12 into 8, that is 2.08 meter per second. Hence providing 12 rectangular barrel 8 meter wide and 2.5 meter height. For the second step, we will design the canal waterway. Provide canal width is 50% of initial width at cross segment. So here in the second step, design of canal waterway. So if you will guys, you will get 2 marks for this also. So here normal width of canal, here normal bed width of the canal is 30 meters. So of canal is 30 meter. So let the width be reduced to be reduced to 50%. That will be 50% of this, that will 30 minus 0.5 into 30, which will be equal to 15 meter. Now velocity through canal, will be equal to discharge by area, that will be the breadth into the height, which will equal to 50 by, for the discharge of canal is given 50 cubics. So 50 by B is this 15 into height is H is the full supply depth is 1.5 meter. So here 1.5 this y. Okay, so now 50 divided by 15 into 1.5 is equal to 2.22 meter per second. This is less than 3 meter per second, so this will be okay. Now here in the design step of the siphon aqueduct, the velocity through canal must be less than 3 meter per second. Only then we can design this canal waterway for this width. So here now this is the plan of a waterway. So this will not be the display of this OP stream, so will not be less than 2:1 for display. So here this will be the river, okay, this will be the river flowing, and this is canal. This is the plan of the structure. This is total width is 30 meter of canal, and this is 15 meter. The width of canal is 30 meter and the reduced is 15 meter. So this is 15 meter and this is again 30 meter. A display of 2:1 is provided in contraction, and a display of 3:1 is provided in the expansion. 2:1 in contraction and 3:1 in expansion. 3:1. And the length of the waterway we have calculated here in the first step, that is 112.5 meter. So length of the waterway here is 112.5 meter. Provide a display of 2:1 in contraction while contracting. So in contraction, so the length of the contraction transition is equal to total 13 minus 15 into 2 by 2, which here the length of the contraction transition is equal to 15 meter. Now we will calculate those. Now we will provide a display of 3:1 in expansion. So the length of the expansion transition will be equal to 30 minus 15 by 2 into 3. So this 30 minus 15 divided by 2 into this 3, which will be equal to 22.5 meters. So the length of flume rectangular portion of canal between abutments is equal to 112.5 meter, that is provided in transition. The side slope of canal section shall be warped in plan from original slope of 1.5 horizontal is to 1 vertical to. In the third step, we will design the bed level at different sections using all these formulas. So now, design of a bed level at different sections. So for this, we will get 4 marks. Okay. Now, so this is the plan section of the flumed rectangular. This is 1, 1, this 2, 3. We will calculate all those for these different sections, okay, from 1 to 2, 2 to 3, 3 to 4. So this is canal. This total is 30 meter. This total is 30 meter. This and this is 15 meter. So here 30 meter, 15 meter, and this is again 30 meter. This is canal and this here is drainage. 15 meter length of the contraction transition is 50 meter, where the length of the expansion transition is 22.5 meter. This is 22.5 meter and this is 112.5 meter of the drainage, that is 112.5 meter. Here the head loss for the contraction is equal to V2 square minus V1 square by 2G into 0.2, and for expansion we have HL is equal to 0.3 times of V3 square minus V4 square divided by 2G. This is the formula for the contractions and the expansion head loss at the different sections. Now at section 4, when canal returns to its normal sections, we have known conditions as follows. Known conditions as follows. So here the area of the trapezoidal section, area of trapezoidal section, sections, we have B plus, we have by plus zy square, which is equal to b plus zy into y, which is equal to 30 plus, since z is 1.5 into this full supply depth is 1.5 meter. So here 1.5 into 1.5, which will be equal to 30 plus 1.5 into 1.5 times 1.5, which is equal to 48.375 square meter. Now velocity for this velocity at the V4 at the 4 is equal to Q by A, which is equal to discharge of the canal is 50 divided by 48.375, which will be equal to 50 divided by answer, that is 1.03 meter per second. Now velocity head is equal to V4 square by 2G, which is equal to 1.03 square by 2 into 9.81, which is equal to 0.055 meter. Now the reduced level of canal bed at 4 is equal to 106 meter, which is given here. Area of the canal bed is 106 meter. Now water depth is equal to 1.5 meter, which is also given. So water depth is 1.5 meter. Now area of water surface at section 4 is equal to area of canal bed plus the water depth, which is equal to 106 plus 1.5, which will be 107.5 meter. Area of total energy level at 4 is equal to this area of total energy level at the section 4 is equal to this plus velocity head, that will be 107.5 plus 0.055, which will be equal to 107.5 plus 0.055, that is 107.255 meter. 107.5 plus 0.055, oh sorry, 107.555 meter. Now so we will calculate this for all the sections. Now at section 3, assuming the constant depth throughout the channel. So here throughout the channel. So we have rectangular sections at 3. We have at section 3 a rectangular channel. So bed width is equal to 15 meter given. Bed width is equal to depth is equal to 1.5 meter, assumed constant here. So area will be equal to bed width into the depth, that is 15 into 1.5, which is equal to 15 into 1.5, that is 22.5 square meter. Now velocity V3 is equal to discharge by area, which is equal to 50 divided by 22.5, 50 divided by answer, that is 2.22 meter per second. Now velocity head at expansion V3 square by 2g, which is equal to 2.22 square divided by 2 into 9.81, which will be equal to 0.25 meter. Now assuming that the loss of head in expansion from section 3 to 4, from section 3 to 4 is taken as HL is equal to 0.3 times of V3 square minus V4 square divided by 2g into divided by 2g, which is equal to 0.3 times V3 is 2.22 square minus V4 we have calculated as 1.03, which is 1.03 square divided 2 into 9.81, which is equal to 0.059 meter. So now RL of TEL, total energy line at 3 is equal to RL of TEL at 4 plus loss in expansion. So this plus loss in expansion, that will be 107.555 plus 0.059, which is equal to 107.614 meter. Now RL of water surface at section 3 is equal to 107.614, which is the RL of TL at 3 minus 0.25, minus 0.25, which is the velocity head, which will be equal to minus 0.25, which is equal to 107.364 meter. Now RL of bed level at 3 is equal to this RL of water surface minus the depth flow, which is 105.864 meter. We have formula: water surface elevation is bed level plus depth of flow, and the energy line is water surface elevation plus velocity head. Downstream energy is equal to upstream energy minus head loss. So we will use all this formula while calculating this. Now again at the section 2. At section 2 we have V2 is equal to V3. Then here the velocity will remain constant, V2 will be equal to V3. So here from section 2 to 3, the trough section is constant. Therefore area and velocity will be same. And 2 2 are same as 3 3. Here between 2 2 and 3 3, between these sections there will be the friction loss, which can be calculated from the Manning's equation. So here there is friction loss between 2 2 and 3 3, which may be computed from the Manning's formula. So here friction loss is equal to n square v square L divided by r to power 4 by 3, which is equal to, so the value of the ruggedity coefficient is 0.015 and is here, n is ruggedity coefficient. So n is equal to 0.016. This v is the velocity and L is the length of the channel. So L is length of a channel. Here L is equal to 112.5 meters. So L is equal to 112.5 meter. Also we have, for this hydraulic depth, we have R is equal to area by perimeter, where A is equal to breadth into the depth, which is 15 into 1.5 divided by the total perimeter we have. Here this perimeter is equal to breadth plus 2y, which is 2 into 1.5. That will be equal to this velocity in trough section. V is equal to discharge by area, whereas discharge is here 50 and area is 15 into 1.5, that is 22.5, which will be equal to 50 by 22.5, that is 2.22 meter per second. So we have all the values here. Now we will calculate the friction loss, that is n is 0.016 square into v is 2.22 square into length is 112.5 divided by r is here 1.25 power 4 by 3, that is 0.105 meter. So 105 meter. Now we will calculate the RL of TEL, water level and bed level. So we have discussed all these formulas in the design stage. From that we have RL of TEL at 2 2 is equal to RL of TEL at 3 3 plus head loss in trough. Head loss in trough. So RL of TEL at 3 3. Here the RL of TEL at 3 3 is 107.614. So 107.614 plus head loss is 0.105, which is equal to 107.614 plus 0.105 is equal to 107.719 meter. Now RL of water level at 2 2. Water level at 2 2 is equal to this RL of TEL at 2 2 minus 107.719 minus the velocity head, whereas the velocity head will be same, that is 0.25. So minus 0.25, which will be equal to minus 0.25 of bed level. Bed level at 3 3 is equal to RL of water level 107.469 minus depth of water, that is 1.5 minus 1.5. So this is 105.969 meter. At section 11. At section 11 we have V1 is equal to V4, since this is that trapezoidal section. So loss of head in contraction transition from section 11 to section 22 may be taken as actually is equal to 0. This head loss is equal to 0.2 times of V2 square minus V1 square by 2. So now loss of head in contraction transition from section 11 to section 22 is HL is equal to 0.2 V2 square minus V1 square by 2g, which is equal to, so V2 is here, velocity is 2.22 and V1 is V4. So 2.22 square minus V4 is 1.03. So 1.03 square by 2 into 9.81 into 9 meter. Now RL of TEL at 11 is equal to RL of TEL at 22 plus head loss, which is equal to RL TEL at 22 is 107.719 meter. So 107.719 plus head loss is 0.039. RL of water level at 11 is equal to RL of TEL at 11, that is 107.758 minus velocity head. So velocity head will be same as V4. So we have, for the V4 the velocity head is 0.055. So 0.055. Now RL of bed level at 11 is equal to RL of water level at 1, that is 107.703 minus water depth, that is 1.5. These levels will be now plotted and shown in figure. So here all these levels are plotted and shown in below figure. So now we have the bed level is 106.203. So 106.203. This is section 1, section 4. Now RL bed level at 11 is 105. 105, this 105.969. Now this is section 2. Okay, this is section 1, this is section 2. Now 33 at 33 105.864. So at 33 105.864, 105.864, and at 44 at section 4 RL of bed is 106, which is given 106. So this is 106. This is section 3. This is plotted for the bed. Now for the water level. So for the water level we have at section 1 107.703. So 107.703, and the total energy level is 107.758. 107.758. Now at 2 this water level is 107.469. 107.469. So 107.469, and the total energy level is 107.719. So 107.719. For section 2. Now for section 3 we have, for section 3 water surface level is 107.364. So 107.364. 107.364, and total energy level is 107.614. 107.614. Now at section 4 bed level we have calculated water surface is 107.5. 107.5, and total energy level is 107.555. So 107.555 meter. So this is plotted for the bed, this is for the full supply level, and this is for the total energy line. After plotting this, we will go in step 4 for calculating the expansion and the contraction transition. For that, step 4 we will design transition. So here design of transition, there will be contraction and expansion transition. So for contraction transition we will use the Mitra's formula, that is contraction transition. Here this Bx is at any distance x. This is breadth, this total is B, and this is the normal width of the canal, this is the length of transition, and Bf is the width of the flume sections, where Ex is width at any sections at a distance of x meter from the flume section. So now we will use the formula. Since the depth is constant here, depth is constant, the transition shall be designed, the transition shall be designed on the basis of Mitra's hyperbolic transition, Mitra's hyperbolic transition equation, which is given by Px is equal to Bn into Bf into Lf divided by Bn into Lf minus x Bn minus Bf. So we have calculated this is the length of the flume sections at step 2, that is, so in step 2 here length of expansion transition is 22.5 meter, where the length of the contraction transition is 15 meters. So for contraction we have Lf is equal to 15 meters. So here Pf is equal to 15 meter, Bn is equal to 30 meter, and Lf is equal to 15 meter. Since here we have here Bn is 30 meter and Bf is 15 meter for the transition, for the contraction, this is for contraction, this is 30 meter and this is 15 meter, whereas Lf is calculated in step 2, that is 15 meter for the contraction. Now we will use this formula. Therefore Bx will be equal to Bn is 30 into 15 into 15, 30 into 6750 divided by Bn into Lf is 30 into 15, that is 450 minus x times of Bn minus Bf is 15. So this is 15x, which will be equal to if we will take 15 common, 6750 divided by 15 will be 450 divided by 15 is 30 minus x. So for various values of x, lying between 0 to 15, lying between 0 to 15 meter, various values of B are worked out, as shown in below table, the distance x is measured from the fluid section, measured from fluid section 2. So here now x and bf, for the different value of x we will get the different value of bx. So from between 0 to 15 meter we will take at the interval of 2, 0, 2, 4, 6, 8, 10, 12, 14 and then 15. Now we will set this equation in calculator. So here we have calculated the value of Vx for the different distance between 0 to 15, and now we will calculate for the expansion transition. For that we have breadth of the fluid section 15 meter, b, and breadth of the channel is the normal width of canal is 30 meter, the normal width of the fluid section is 15 meter, and the length of transition is 22.5 meter, which we calculated in a second step. In the second step here 22.5 meter. So now we will use this Mitra's formula to calculate the value of breadth at any distance x from the fluid section. So we get this 675 by 45 minus x. Now the value x lying between 0 to 22.5 meters. So we will calculate this for the interval up to here also 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22.5. So here 675 by 45 minus x. 45 minus x. So for 0 we get 15, for 2 we get 15.69, for 4 we get 16.46, for 6, and for 22.5 we get 30. So this is all you need to solve for this numerical if you are asked in the exam, and this is almost out for 8 marks I think. So after solving all this you will get the total marks, and all the best for your exam. If you have any query you can just ask in the comment box. Thank you so much for watching my video.